circular motion. So today we will continue with a centripetal force. This is a force which make an object to move in a circular path. So we say that it's a force on the object which makes it to move in a circular path. But this force does not tell us which causes this to happen, which might be gravitational, electrostatic, magnetic, friction, or whatever. For example, if a car is making a corner, we say centripetal force is caused by friction on tires. Also, for example, for the Earth, the gravitational pull of the sun provides the centripetal force that is move in its orbit. So for the Earth to move in its orbit, its centripetal force is caused by gravitational force. And for a car making a corner, centripetal force is caused by frictional force. So that's why I say this centripetal force can be caused by gravitational, electrostatic, magnetic, friction, or whatever. So it depends. So now let us see how we can calculate acceleration and force when an object is moving in a circular motion. So for example, this is a motion described by an object, and this is a center. An object is here, let's say object A. So it's moving in a velocity VA at point A. At point B, the velocity will be VB. So if you find the angle here, this point will be angle theta. So it means that the velocity is changing as it goes, as the angle increases. So if we take these velocities to be velocity A, velocity B, and this is the change in theta. So our change in velocity will be change in V. So now these are relevant because the speed is constant to be V, let's say V. So now our theta is given by change in V over V. If you divide by time both sides, change in T over change in T, this will be change in T over change in T. But so if you divide here, it will be V change in theta over change in T, which is equal to change in V over change in T. At change in theta over change in T, this is omega. And change in T over change in time, this is acceleration. So our acceleration is V omega. V omega. But remember, so we can find our acceleration by using this formula. Speed times omega. But remember, our omega, our V, relation of V and omega is omega times radius. So here our acceleration will be, if you put here for the v, if we put omega r times omega to be acceleration is equal to omega square times radians. So this is also our new formula for acceleration for a body moving in a circle. Also, we can write our formula by using only v. So our acceleration here, we can remove this omega by letting this relation. So our omega will be equal to v over r. So now v times omega, which is v over r. So our acceleration will be v square over r. So this is how acceleration can be found. Now, by using Newton's second law of motion, we can deduce an equation for centripetal force. Newton's second law of motion is force times mass is equal to mass times acceleration. So force, now centripetal force will be equal to mass times v square over r. So this is our formula for centripetal force, or mass omega square r if you want to use omega. So this is our centripetal force. How we can find centripetal force? By knowing the acceleration of an object in a circle. So now, because we have known the centripetal force is equal to mv square over r, so let I use this force to calculate the orbital speed of the S. Orbital speed of the Earth. Yeah, we say that centripetal force of the Earth is provided by gravitational pull. So mv square r, we say that centripetal force is provided by mg. So mv square r is equal to mg. So this mg is gravitational pull. For the S to move in its circular path, its centripetal force is provided by gravitational pull. So now m and m will go. So v square will be equal to rg. So our orbital speed of the S will be equal to under root of radius and gravity. The radius of the S is approximately 2 6.4 times 10 6 meter, and our G is 9.81 meter per second square. So our orbital speed will be equal to 6.4 times 10 6 times 9.81 root. So our orbital speed will be equal to 7.92 times 10 3 meter per second square. No, meter per second. So to write in kilometer, this can be 7.92 kilometer per second. So this is our orbital speed is the orbital speed of the S. So we say that if you were to throw or hit a ball horizontally at almost 8 kilometers per second, it will go into orbit around the S. If we throw an object in this velocity, which is around 8 kilometers per second, it will go in a circular motion in S's orbit. It will not come back. The origins of centripetal force. For example, for case 1, the car cornering on a level road. A car cornering on a level road. Here we say the road provides two forces. For example, this is the road and this is the car. Now the road provides two forces, which is the frictional force and also the normal contact force. The normal contact force, which we say N. And remember, this car has its weight which pulls down. So the normal contact force is balanced by weight. And also we have the frictional force, which is Fr, frictional force. So now our centripetal force is caused by frictional force. Our centripetal force is caused by frictional force. So the frictional force will be equal to centripetal force, because centripetal force is caused by frictional force in this case. So, but remember that our frictional force, it means a force in contact of the tires of the car, which is normal force. But a normal force is balanced by mg. So now our normal force N will be equal to centripetal force mv square r. But N, which is contact force, is balanced by mg. So our mg will be equal to mv square r. So g is equal to v square r. At this point, you can find even the velocity of the car to make a corner on a level road. A car cornering on not a level, now it is rough, which is banked road. On a banked, this is a road which is in a certain angle. It's not level, it's not smooth. A car cornering on a banked road, here is normal contact force has horizontal component which can provide centripetal force, and the vertical component balance the car's weight. So now our road here is not level. It's not leveled. So it's like this. So we say that it's inclined on a certain angle. So then this is our car. This is our car, where the normal force now is sway, and its weight is mg. See? If we resolve this angle, find that this angle is equal to this angle, theta. So and our centripetal force to make a corner is here. So we find that we take this to be equal to so find that if you want to take this part here, our horizontal is this side, which is centripetal force, and our hypotenuse will be normal contact force, and this will be our adjacent, which is perpendicular, a normal contact force. No, it's a weight. This is a weight. So if we want to find the centripetal force here, we say, this is the opposite and this is hypotenuse. We say now tan theta is equal to opposite, which is centripetal force. This one, centripetal force over hypotenuse, which is n. So now our n and theta will be equal to centripetal force. That's why we say here the horizontal component will provide centripetal force. So our centripetal force n times theta is equal to mv square over r. So we can continue with here this point. And if we want to find the vertical component, we find vertical component here. Cos theta is equal to from Sotoka Hahi is equal to adjacent of hypotenuse. So our adjacent here is mg, our hypotenuse is n. So n cos theta is equal to mg. But our main objective here is to find the source, or which force, which component will cause a centripetal force, which will make this car to make a corner on a bank road, which is this one. So this is a very important formula to find the speed of a car to make a corner on a banked road. This is very important. On a banked road, the horizontal component of the normal contact force from the road can provide the centripetal force needed for the cornering. So centripetal force is equal to normal contact force times sine theta. Thank you.